Hello and welcome back. Today we'll be doing question 3 from the 2001 Step 1. Let's get started. Question 3. Sketch, without calculating the stationary points, the graph of the function f of x given by f of x equals x minus p, x minus q, and x minus r, where p is less than q is less than r. By considering the quadratic equation f primed of x equals 0, or otherwise, show that p plus q plus r all squared is greater than 3 of qr plus rp plus pq. By considering x squared plus gx plus h multiplied by x minus k, or otherwise, show that g squared is greater than 4h is a sufficient condition, but not a necessary condition for the inequality g minus k all squared is greater than 3 of h minus gk to hold. Pause the video to have a think, and once you're ready, restart to see if you were correct. Let's get started. To start with, we'll notice that they've given us f of x already factorized, meaning that we can sketch it very easily. It must go through the points p, q, and r in this order, because p is less than q is less than r. We'll also notice that the coefficient of x cubed is 1, which is greater than 0. Which means that the cubic will go from negative infinity on the right up to positive infinity on the right. We can therefore sketch a quick graph of f of x passing through p, q, and r. Now we can move on to prove that p plus q plus r all squared is greater than 3 of qr plus rp plus pq. First, we'll notice that p, q, and r are all roots of the original cubic, which you shall write as f of x equals x cubed plus bx squared plus cx plus d. By Vieta's formulae, which is roots of polynomials in the A-level syllabus, we now need to prove that negative b over a all squared is greater than 3 of c over a. Since a equals 1, we therefore have b squared is greater than 3c, which is what we need to now prove. Now, we'll notice that f primed of x is 3x squared plus 2bx plus c. As the cubic has two distinct turning points, the discriminant 4b squared minus 12c must be greater than 0, and therefore b squared must be greater than 3c, as required. Now we can move on to the final part of the question. By considering x squared plus gx plus h multiplied by x minus k, or otherwise, show that g squared greater than 4h is sufficient but not necessary for the inequality g minus k squared greater than 3 of h minus gk to hold. Firstly, we'll write capital F of x equals x squared plus gx plus h of x minus k. This is equal to x cubed plus g minus k of x squared plus h minus gk of x minus hk. We'll then find capital F primed of x equals 3x squared plus 2g minus k x plus h minus gk. If g squared is greater than 4h, then f of x has 3 distinct roots, meaning there are 2 distinct turning points. This means that 2g minus k all squared minus 12 of h minus gk must be greater than 0, and therefore g minus k all squared is greater than 3 of h minus gk, as required. Now, to show that g squared greater than 4h is not necessary for g minus k all squared greater than 3 of h minus gk, we merely need to find a counterexample, such as g equals 2, h equals 1, and k equals 1000. And that's our answer. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.